In this lecture, we'll walk through an exercise in reducing code complexity per the complexity metric discussed earlier. For our example, we'll use a program to identify sorted sequences within a series of input integers. We'll implement this program using the IHS interface for coding exercises. And that's IHS version 1 as of this writing. You may hopefully have a better version by the time you view this, but it will have the same functionality. If you haven't already, please register as an IHS user and enroll in the course IHS workbook for coding elegance, in which the sorted sequences problem should be the first exercise, like you can see here in the current courses workbook for that. Read the IHS documentation for coding exercises, which will be linked from the first exercise. I'll bring up the IHS v1 version of our problem here. And there's the link for the documentation for it as well. Now, as the problem description here indicates, what we are supposed to do is write a program that reads a series of integers and reports how many sorted sequences, that's sequences of rising or equal value, there are in the series, and the length of the longest such sequence. Now, be sure you understand the spec, and also look at the test cases, as you should always do with any IHS coding exercises. Those test cases are there to elucidate the spec as well as to test your code. Here's an example of what we're talking about. There is a rising sequence 1, 2, 3, 3, another one 2, 3, 4, 4, and then 3, 4, 5, and the output indicates that there are 3 sorted subsequences and the longest has 4 integers. And so that's what we're going to be doing. Now, with the task at hand understood, let's try a first solution for it. And have one arranged here that does the job. So let's take a look at this before we submit it. It's a reasonable, if somewhat wordy, implementation. It reads a first integer to be sure there is one, and tests to see if the read succeeds, right here on line 7. Assuming there is at least one integer, it then loops on lines 9 through 22. In each iteration of that loop body finds one sorted sequence. Sequence count counts the number of such sequences found, and as you can see is incremented here, and this length tracks the length of the sequence currently being found. The inner loop on lines 11 through 19 endlessly scans for a next integer, and if that scan succeeds and results in an integer that is still in ascending or equal order with the prior integer, then we make the new integer our prior for the next iteration, and we increment this length to reflect the longer sequence. Otherwise, we break out of the sequence tracking loop, copy next, which is now the start of the next sequence, into prior, and we update our statistic for longest sequence. And then finally, on lines 25 to 32 here, we deal with the special requirement that we use one and singular form when there is only one sequence, or when there is only when the longest sequence has only one integer. And the result is a four-way branch with a different printf in each case. That's kind of irritating, and it has attendant code complexity, as we will find out, not to mention some pretty long lines. Well, let's take our inelegant solution here and submit that to IHS and see what we get. So there it is, and looks like our code has a total complexity of 150.5, which doesn't really even meet the low bar of 110 for this problem, and it sure doesn't meet the high bar, the better bar of 96. So let's improve this code step by step. Now, you may already see lots of ways to improve it, and you should feel free to strike out on your own at this point if you like, getting it down to that 96-point target. But if you prefer, here's a more guided approach in the form of in-lecture questions, working from the top of the program downward. Let's start with merging some control structures here. It's remarkable how often people will do a general test prior to a while loop when the loop itself could take care of the test. So with that in mind, question 1, this if on line 7 is redundant. Given the while just under it, how can we remove it? Coming back from a pause on there, well, really all we need to do is just drop line 7 altogether here. It is redundant because the while loop won't execute if res is not equal to 1 anyway. So we can do that. And let's see what we get for lower cost as a result. And we are down to 145.5. So that bought us 5 points. And now it's just under 50 more to go. So let's see here. The next possibility. As the prior lecture on code complexity pointed out, break statements are not cheap. And indeed, some shops would summarily reject code like our little endless for loop here in a code review. Let's redesign that loop into a while with a test that continues the loop as long as the sorted sequence continues and has no break statement. So question 2 is to do that redesign. You may find that you need to duplicate the scanf call to make it work. And that's okay, for now at least. We'll fix it in the next step. So coming back from a pause there, what we want to do is take the test and run that up into the while loop here, or the for loop, which we will make a while loop. And then we will take the res equals scanf line and duplicate that both above and at the bottom of the while loop. And then we can get rid of a lot of additional lines here. Most importantly, the break, and end up with a nice clean while loop, with our scanf being done both in advance of the test and also at the bottom in preparation for the next iteration. So let's see what that gets us. We'll submit it to IHS here. And we see that our complexity has gone from 145.5 to 133.5. Okay, that got us a nice 12-point improvement. It's a shame to have to duplicate the scanf, but it's certainly worth it to be able to ditch the break and the inner if-else, especially because they're multiplied by 1.2 being nested inside a loop. Okay, so let's get rid of the extra scanf. If you use an assignment as an expression within the while test, you can do this pretty easily. And under our complexity rules, that counts as a good use of an assignment expression, so you'll only be charged 1 point for it, not 4. And so question 3 is to reduce the complexity by removing the duplicate scanf. Coming back from a pause there. Well, the way to do this is to take the, I'll just edit the IHS directly here, take the scanf equal next call, and drop it straight in the while loop there with a 1 equal test. And that way that single scanf can serve for both the first iteration and for any successive iterations. Thus, and submitting that to IHS gets us a improved complexity of down to 127 now. So another, what, 7.5 points? It's pretty good. And this is about as far as you should go with nested assignments, lest you trigger the 4-point rule. And it's good style, as I did in my answer, by the way, to put the 1 equal at the beginning because it makes it clear that you're testing the results of the assignment expression, and it also causes a compile error if you neglect the needed parentheses around the assignment. So we're down to 127 points, and we have just 33 to go. The next step here is to look at the conditional operator for updating longest. The lecture on code complexity showed that a conditional operator is priced to be cheaper than the equivalent if-else, but this is only true if we need an else. So question 4, rewrite the update of longest using an if instead of the question mark colon. Coming back from a pause there, this is what we need to do. If this length is greater than longest, then longest equals this length. A simple if can replace the question mark colon, and the result is about 5 points saved. If you're using a conditional operator when one branch is just a no-op decision, a small if statement is clearer and cheaper per our rules. If you count out the points, the question mark colon costs 12 points and the if statement costs only 8. By the way, question 5, just to be sure we're alert on all the rules here, if we reduce the complexity by just 4 points, 12 for 8, why did it drop by 5 points? And coming back from a brief pause there, I hope. Well, the code in question is in a loop, and thus it gets a 20% surcharge. Simplifying loop bodies is a bit more valuable than simplifying code outside a loop. Okay, our next step, and one of the biggest, is to fix that four-way ugly if-else down here at the bottom. Now, anytime you get in all combinations if-else like this, it's worth trying to refactor it so that each choice is handled by a smaller if-else. In our case, we can break the single printf into two printfs, one for the first part of the line and the other for the second. So question 6, think through how to refactor that if-else block and see if you can get the complexity down by 28 points, reaching the goal of 96 points. You should end up with two much simpler if-elses, replacing the complex four-branch if-else-if. And coming back from a pause, what I'm going to do is this. If we print the output up to subsequence, comma, as one if-else, and then the part after that as a second if-else, then we'll only need to test seq_count and longest one time each, and the printfs will have fewer parameters and shorter strings that don't exceed the 40-character extra cost long string charge. And submitting that, we can see that we have reached the optimal cost of 96 points, actually 95.2, and so we're done. Now, this is just one example of the sort of code improvement you need to do to meet the complexity standards in many of the IHS exercises. As you do exercises like this, focus on finding many different ways to write the same code. It's not a matter of finding the perfect way the first time, so much as having thought of a variety of ways to do the code, and then picking the best one from them. And remember that the investment in elegant code will stand you in good stead in professional work. In both job interviews and internal code reviews, elegant, concise code commands respect.